most of it will be about that size. All right, second lecture. We're going to look at some of the physics of the Feynman approach to quantum mechanics and symmetry. The idea of the axioms that Feynman has, number one, will occupy a good part of this lecture, but then the other three, axiom 2, 3, and 4, all have connections that can be explained very nicely with these beam analyzers that we've been talking about. So we're going to use that to develop, and then we'll come back and show in the next lectures a mathematical dovetail between these ideas that we're using to develop quantum mechanics. The basic idea that physicists have is that the world is described by mathematics, but unfortunately mathematics and physics have gone through a messy divorce. So nowadays it's very common to have a mathematician that doesn't even really understand Newton's first laws, let alone the things that go with quantum mechanics. And of course it's quite common to have physicists that really are very ignorant of mathematics. And so I think what Feynman wanted to do was bring them closer, and that's what we're trying to do here, is make it so you can think with the same part of your brain about both and make the tools work for you better. So today we're going to show, as I said, a little bit more of the physics. Now I want to just quickly review and make sure that you don't have any questions about what we did last time, but then we'll get right into a question that I have always found amusing, and that was, did Max Planck goof? And he thought he had. He became very depressed after he presented his axioms for the energy quantization. So we're going to discuss that in a quantitative way and answer questions like how much energy is one photon worth. But this all ties in with Feynman's amplitude, and these are things that Feynman doesn't do in his lecture notes, volume 3. At least not in a detail we're going to do it. Now, what I would also like to get started on is not just these simple sorters like our calcite crystal here. I want to do a sorter and an unsorter, which makes what we call an analyzer. So that will be midway, more or less, in the lecture today. And we will talk first about the do-nothing analyzer. That you have to get that idea in your head. It's a little hard to visualize what the waves of light are doing inside these devices that we're trying to represent by our simulations. And then finally, I hope we'll get to the do-something analyzer, something that really has an effect on an incoming state, whether it's an electron spin, which is the usual thing people talk about, but as I've said, polarization is more down to earth, something you can visualize what's happening more easily. So we'll use that when we come to talk about the analyzers first to make it understood. An analyzer can be a sorter like this. It's easy, just let it do one side of it. It can be a filter like the Polaroid sunglasses we talked a little bit about, or the Brewster polarizer. It can be a half wave plate, a quarter wave plate, a third wave plate, any number between well, basically 0 and 2 pi when you're thinking about the angles of things. And we'll get into that in great detail at a certain point much later on. Anyway, the first thing I just want to make sure that the idea of abstraction and all of the transformation stuff we did last time If you have any questions about that, this would be a good time, since here is the two sides of our story, and also the beginning of a transformation matrix as a coordinate changer. That's the next slide here. If you recall, we were getting the components of a given state either in terms of x and y, or else in terms of x prime and y prime. So these coordinates here are obviously very different from these coordinates that have the finer dot structure. And the question is, how do you transform the x prime coordinates into the original coordinates, or how do you take the original coordinates and convert them into the prime coordinates? And that's the set of equations right there. Basically, you have a matrix x prime, first component, then the 1, 2 component is x, y prime. This one matches with this one matches with this to make a sum that is that. Okay, so that's what we were deriving. We're deriving matrix algebra. We're going to have a very short and sweet course on linear algebra that I would claim is the best in the world. We're going to do some really funny things with the matrices. That's the mathematical part of this. Some neat tricks. But right now I just want to get the notation down. Okay, so any questions that you can think of at this point? And I would recommend, as you're reading through the stuff, or you know, doing problems, whatever, we'll have a problem today to look at. You make notes. You know, if something you aren't clear on, or it's just something that you find interesting, make a note of it. You know, keep a log. Okay, so let's go and look at Planck's axiom. And it was about light at low temperature, basically, a box of light, what they call a black body cavity. Okay, you remember all of that. This is a 1900 paper, so literally the turn of the century was Planck's paper, 1900, in which he proposed that the energy density, the amount of joules per volume, U, which is equal to some quantum number, integer, times h and frequency, or else h bar and angular frequency. The h without the 2 pi is equal to this. The h with the 2 pi divided into that is about 1.05 times 10 to the minus 34. So 2 pi is 6.28, which is not too different from 6.63, you see. So remember that this one is the big one that's got 6.63 times a really tiny number, okay? And then the h bar is 1.05 times the very tiny 10 to the minus 34, okay? So just to keep the numbers straight. Anyway, the idea was that this would be the smallest amount of energy per cubic meter that you could have in a box of light of frequency omega. Or if you're talking about a real frequency in hertz, then it would be this h here, the big number, times the number of cycles per second that was giving us the smallest amount of what we call energy. And that's really the beginning of modern physics right there. As I say, he had doubts about all this, and that's what we're going to talk about a little bit here. But the real experimental, shall we say, exhibition of this is when you're actually doing experiments with the very sophisticated devices that we call photon counters that actually put out little blips that counts at some rate that depends on your intensity and all that. We're going to try to quantify that a little bit here today. But what I'd like to show is that I'd like to prove, we've already proved that these amplitudes are sines and cosines, and I'd like to show you very precisely why we're interested in the square of this matrix element. And this wasn't always obvious. When it came time for Ehrenfest to write a paper on the wave function, he had an idea of the wave function that was like Schrodinger's, and this is a little bit later in the game. Okay, it's well after the Bohr business. He actually wrote in the paper that that psi that we're so familiar with was the probability. And he wasn't thinking about a psi that had complex numbers, you see. He wasn't, had nothing in mind about oscillatory things, you see. So he actually said in the paper that psi is the probability. And then in the appendix he says, oh no, psi, it's not psi, it's psi squared. Absolute value squared. And at that point somebody had educated him on so this is really an amazing history of this. You can see how confusing it was. And we're still confused about this. I'm just trying to straighten it out a little bit here. Okay? But anyway, we're going to discuss what this thing here really means with regard to light. And that's what we're talking about here. So it's all stuff that is, as I say, more or less available in tabletop form fairly cheaply. The crystals here can be used, but there are a lot better things that we'll talk about. In any case, the idea that I want to get across here is that the E field vector, now I have to make full disclosure here to remind you that while you have studied electromagnetism, in your case enough to pass the exam, okay, you still have to pause and say, do I really know what an electric field is? We just made that an axiom, right? So, boy, there it goes again. I don't understand that. The powers that be don't like me talking about this. But anyway, there's a secret hidden in the electric field, right? Well, let's just suppose that we're conversant with that. This is the guy we're trying to figure out, right? And what I would claim right here is that this is a relationship which is simply proportional. It's a proportionality, a quantum field proportionality constant that turns the size into an electric field, or vice versa. 1 over F would turn electric fields into what we call psi. So that's what we're going to derive. I want to get that out of the way, you see, to really fix it so that we can make a connection to the mysterious psi that everyone coughs and sputters about in the beginning of whatever quantum mechanics book they write. We don't have to cough and sputter quite as much, except for the fact that we really don't know what the E field is, or the vector and scalar potentials. You're talking about this stuff called charge. What in the heck is charge? And if you've seen that talk I gave, we have a much better picture of what mass is. The charge is still, hiding in there somewhere. How do you make those particle and antiparticles that have opposite charge out of two beams of light? Right? Okay, so just making sure that we know where our ignorance is before we go ahead too far here. Okay? So we got to derive this thing. This is called the quantum field coefficient or proportionality or something like that. We have to derive that. And then we have to talk about what Planck was worried about in his development. So the basic idea is that when we talk about waves going through a beam, this time I'm making the z coordinate, the actual distance along the beam somewhere, say right here to start with, or even down here. But here we're really talking about light that's been polarized nicely So I really know these coefficients pretty well. Classically, I should say semi-classically, because what we're using is a laser, and that's another thing we'll talk about later, but laser in a coherent state is an important idea that needs to be spent a whole lecture at least on. Anyway, this little vector here, two-component complex vector, except for this value f, it's just this. You see, this thing is equal to 1 over f times what we would normally write down if we were just doing an optics course and looking at the x and the y components perpendicular to a beam that is moving with some k vector in the z direction. And most of the time we just make sure that we're doing it within a wavelength or so, and we leave this factor out with just the time dependence at, say, this point right here. We call that z equals 0, and work from there. Okay, so here's the deal. Somehow we've got to show that this idea, it's really Ehrenfest, Born, and a bunch of other people who were developing the idea of probability, which comes down to basically the number of counts per square meter per second. Basically, it's we'll be talking more Poynting flux. But inside a cavity, we'll be interested in the number per volume. The photon number is what this is called, because each quanta has been given the name photon. Every time you quantize something in the physics nowadays, like if you have a quantum of magnetic something or other, you call it a magnon. If you have a quantum of vibration, some people call it a vibron or phonon, right, for the it's a more common name. Okay, so the little word, putting a little suffix on is what we do whenever we're trying to think of the stuff that's going on here in the way Newton did, corpuscles, right? Okay, so here's the square of x and the square of y that's being added up to give us the experimental results for this imagined experiment, which is done many times in this building because we do quantum optics. But let's make a connection between energy density, that's joules per cubic meter in our MKS unit system of a light beam. That would be a nice thing to use if you had a cavity and wanted to discuss the energy density per volume. But if you open the door on the cavity, something's going to come out, and that's going to be an energy flux. That's going to be a Poynting flux, okay, the E cross B, if you will. And these are related very simply by the factor of the speed of light. You can think of a volume of the light moving along at c, and that's your energy flux, carrying the energy density to you, and yet that's what's going to be going on in the photon counting business. We're going to be talking about Poynting flux. So we'll make that distinction when it's important to make it. But the basic idea is the sum of these squares is giving you that flux, or if it's just a cavity, it's giving you how many of those things are waiting to come out. If it was a perfect cavity, of which doesn't exist, that's of course the big problem with all of the quantum optics, is light just can't be perfectly trapped very easily. What we assume it is in all of our thought experiments. Okay, so what we're going to do is we're going to equate the classical value with this constant epsilon 0. Okay, now I don't remember that constant very well at all. I remember this one. I remember that the Coulomb constant, it goes in front of the rule of charge times charge prime, over r squared for force or over r for energy is 1 over 4 pi epsilon 0. And that 1 over 4 pi epsilon 0 is really easy to remember. If you're only interested in, say, three-figure accuracy, it's 9 billion. 9E9. Okay, that's a good, huge number, right? If you have a Coulomb, you're in trouble, right? Huge amount of energy. Bomb, you might say, if you ever got a Coulomb, right? That's what an atomic bomb is, really. It's a bunch of Coulombs trying to get away from each other. Same with chemical explosives. So, we're going to take this classical thing and connect it to this. There's the energy density according to Planck. And that will give us this constant. Okay? That's the job here. Okay? So here we go. We go NH bar omega over whatever the volume of the cavity is U. That's energy per volume. Okay? And we're claiming that is epsilon sum of squares. Okay? That's epsilon, this constant we're after, squared times sum of squares, which we're taking to be the quantum number. Okay? So that's it. We just have to solve that. That's pretty easy, right? Make sense?
Yes.
Okay? N would be UV over h bar omega. We're using the angular frequencies here. Usually turn that into h nu. Okay, so we got epsilon v, then the sum of the squares, which is n. Okay? Now we're going to divide by n. Okay? You get 1. 1 equal uv nh bar omega. That's epsilon v, sum of squares of electric field. Okay? But this is already n, so we divided that out. We just get f squared here. Okay? With these epsilon 0 v h bar omega equal to 1. So there's your quantum field constant. H bar omega over v epsilon 0. Okay? That's basically the quantity of stuff for one photon. And that's another way to write it is it's the sum of the squares of the energy divided by n. Okay, that's for n photons right there. Okay, let's look at some of the numbers that are associated with that. And I also asked the question, did Max Planck move? And here's, as far as I can tell from a little bit of history I know about this, the 1900 energy density U equal h bar, well, he didn't use that notation, h nu n, this axiom, his axiom paper. After he finished this, I don't know, somebody must have said something, or who knows what, but he left in despondence. And he thought he had made a career-ending move. In science, you sometimes can get trashed, right, if you do something that's really crazy. Okay? I've been fairly immune to this. I've gotten away with a lot of crazy things because enough of them worked that it was okay. But anyway, the paradox that I think he had some doubts about was, from his education, he knows that energy for a classical harmonic oscillation is quadratic in the frequency and amplitude as well. Okay? And amplitude here, we really mean the A that goes with the vector potential. Electric field, if you don't have any curl B, then all you have is minus partial with respect to time of the vector potential, which is I omega A. Okay? So in any case, this is the kind of energy expression that Planck was ready for. That is that the epsilon 0 and the sum of the squares, that's what this is right here, the absolute value magnitude of the electric field squared. Epsilon 0 is your internal energy. If you want to use vector potential, which we do later on, that's what you would write. Okay? But, he says, quantum axioms give the field energy and the Poynting flux to be linear in the frequency. Okay? Energy density U in cavity mode is h bar omega n divided by the volume of the cavity, or it's the Poynting flux is h bar omega a little n, that's different, completely different character, because you're actually counting that one. This one is just in there waiting to be counted, divided by beam area. Okay, so that is a problem. So here's a quick resolution, which we have. Given the constant, say n equal 1 quantum field factor squared, that is definitely linear in omega. Okay, this f squared here is linear in omega. Right? So you can write the constant the way we did, for n photons. Okay? So what you're doing is you're showing that this squared quantity, this omega squared a squared, is linear in omega. Now what's going on here? And this is particularly germane for relativity, because the way I do it is I work from the Doppler effects for frequencies. And if I've got two frequencies, that's very different from having one frequency. It's multiplied by an exponential of something called rapidity. So it's e to the 2 rapidity for one and e to the rapidity for the other. So, I would share his despondence if I didn't know better. And what is it that makes this work? Okay, well, this is a quick way to do it. This is the formal resolution of quantum field theory. This Hamiltonian, if you will, for the this thing right here, it's this a squared omega squared, okay? That oscillator Hamiltonian, which can be written this way, or it can be massaged into a combination of creation and destruction operators multiplying each other. And we're going to talk about that later on too, because this is very much a group theoretical exercise, because this Hamiltonian, which if you scale the thing with omega buried in the constants, which is essentially what we're doing here, you can just write this as p squared plus x squared. And you got to factor that thing. So when you factor x squared plus p squared, you get x plus ip, and you get x minus ip. And that's essentially what these things are. Okay, so we're going to do that in great detail. That's the way we develop a lot of our formulas for group theory. It's using that sort of factoring. And that's what group theory is really about for mathematicians. It's the ability to analyze the factoring of polynomial equations. That's how Galois really got started and took off on the work of Abel and a bunch of other mathematicians. He made his, this is, when I'm thinking of the group theorists, and now the name has slipped my mind, Galois. Galois theory includes group theory. And it was mostly aimed at solving polynomials. That was a big deal in the mathematics of the late 1800s, a big deal for a long time. So we'll talk about that later on, but this is an example of using polynomials to analyze symmetry, and in this case, physics, of a very highly symmetric Hamiltonian, where you can interchange momentum with position and it's still the same thing. That's an incredible symmetry. So the number of dimensions of this oscillator, if it's 2 dimensions, that's a group unitary 2. If the oscillator is 3 dimensions, that's unitary 3. If you put 4 dimensions on the thing, because you have 4 particles, or however you do it, you got U4, you see. So this is an extremely, shall we say, royal group. It takes care of a lot of stuff. Its subgroups include just about all we're going to talk about in this course. They're all subgroups of that. We talk about translation. It's a little bit outside, but they also can be made to fit in that bailiwick. All right. So you then get an eigenvalue for each dimension of a harmonic oscillator as h bar omega n. Oh, plus a little bit. What they call the zero point. Okay? Now that's for each dimension. And we've got two dimensions, x polarization and y polarization, right? So I got 2 halves. So I got a 1 here. Okay? And so if I don't have any n, then the energy of that vacuum is h bar omega. No half, no nothing, no half and half, right? It's h bar omega times a half plus a half. Okay, so all this stuff we've been doing, equating h bar omega n, is exactly right according to this. That's why I brought it up, because this is a formal resolution. This is kind of waving your hands, right? Classically. This is the actual quantum thing. So you can take this to the bank as far as making Planck happy. He's so depressed, and so he's willing to buy it, right? So that I want to point
is there
out.
a relation between the formal resolution and quick resolution? I cannot see any.
Oh, say that slowly.
I cannot see any similarity between formal resolution and quick resolution.
Oh.
What is the relation between harmonic oscillator and
this
that
quick
one?
resolution was lucky. It's classically right, except I've got to take his axiom, right? And so the question is, what is n, you see, for the formal, right? Formal, we really know what a quantum number is, right? So at first, if light only had one polarization, he'd have to put a half on that. Or you have to subtract a half from it, depending on what you're counting, right? But since the actual answer for 2 dimensions is going to be 1 for x and 1 for y, and each of them have, say, the same frequency.
Sorry, I cannot see the. No,
then it would be 1.
I cannot see the point between E, E2, and X2 and P2. I cannot see the relation between these two.
Between this one,
yeah,
and this one.
Yeah.
Okay? Here's the relation.
Yeah.
This one really should be, if you're counting, saying how many photons do I have in there, and call the vacuum 0, you see, this should be written in +1, because if I put a 0 here, that says I don't have any energy at all. And we know that's not true.
That's not true.
Okay, especially if we've done this.
Oh.
Right?
You mean that Max Planck?
Yes. Max Planck, he didn't know any about this.
Yeah.
Right? That came much later. I mean, that's 1930s almost, right? That came much later, okay? So the n that he's getting is the actual number of the live photon, not the dead one that you have in a vacuum, the 0 point guy, okay? So he was lucky, this is lucky, everything's lucky to be exactly quantum, even though, what the hell are we doing here? This is pure luck. So that n never goes to 0. It's really the quantum n +1. So when you have a vacuum, you got a 1 there, not a 0. Yeah. Does that make sense? Yeah. Subtle point. Okay. Thank you for questioning. I'm sure people watching this are asking the same thing. Okay. Now, we ought to look and see what numbers are. Okay. It's kind of interesting. Example. Suppose I had a 1/4 micron cavity. Now, that's, about 600 terahertz. That's a half wave for 600 terahertz green light. Okay. And we'll talk about, say I have 1 million. That's not a lot of photons for some of our cavities now. That's just a sort of getting a laser going. It takes that much in a cubic 1/4 micron cavity. Put the numbers into that, okay, using this. And we'll talk about one photon as well. That is of interest, okay? So the energy per photon that we're going to, as we build this thing up, and that means the energy that we start with, because this is n plus 1 in the quantum net language, is this 6.63 times 10 to the minus 34 joule seconds. And remember, this is the big H. Okay, times 600 hertz, which we're talking about here, not radians per second. And we're going to have let's see if I've got that right. Yeah, 600 terahertz is green light. Okay, so that's 10 to the 12th. Well, that comes out about 2 1/4 electron volts. So that's one photon has a quarter, 2 1/2 electron volts. That's what you would literally be talking about. If you take all of that, no matter how big the volume is, you take the whole photon, eat it, you have just gained 2.5. Now, electron volts, that's kind of a weird unit that has to do with the charge of the electron, right? 1.6 10 minus 19 to define it, but it's one we use a lot, so I thought I'd put it here. 10 to the minus 19 joules is, you know, looks kind of small, and it is. E field for one photon, how big is the E field? Look at that, one photon gives you a million volts per meter. Now remember, you're talking about a cavity that's really tiny, and the electric field is a million volts if I go this far, but if I bring it down here, you see that it's not that much voltage, but it's not really small. It's not astronomically small. I think that's worthwhile noting. That's your electric field right there. Million. One. One. Okay, now stick in the usual number, you're talking about 1 million electron volts. Okay? 2.5 times a million electron volts. Okay? That's you know, worth knowing. Now I have reference sightings here for some more of this kind of numbering, but I want to go on. Now, we can ask again, was Planck's linear in frequency energy axiom a goof? And I'm claiming not at all. It's really not linear. This energy is really not linear in frequency. His axiom is not linear in frequency. The epsilon E squared equal Hn frequency has two frequencies in it. And this is important because when you go to suck this cavity out, you're going to count so many per second, or so many per second per square meter, or something like that, right? So you have two frequencies here. One determines the color, the other determines the quantity. And that's a frequency too. And it will Doppler shift just like this frequency. If you run toward that cavity, you're going to see a higher color, that is, a red will become bluer. You also hit more of these things, right? The frequency of being hit is going to Doppler shift just like the harmonic frequency that's giving the color. This, I've never seen anybody say this. Even Feynman didn't say this. But I think it needs to be said. Because immediately it lets you show, this is something we'll do later, both frequencies transform by relativistic Doppler factor, e to the rapidity, plus for going blue shift, minus for going red shift. The coherent frequency of light, which is the quality, is going to shift by that factor. The incoherent frequency of light quantity also going to shift. And this is E squared, so that immediately says that the E field will transform like a frequency. And it is a frequency, because as you stack up, you're talking about the frequencies that you've added up by putting more photons in. So this means that the electric field should transform under Lorentz transformation by exponential of the rapidity. Now, if you go back and do all of the field stuff that you need to do in relativity, involving the field tensor that has the electric field and magnetic field, exactly what you get for a plane wave. So when I first saw this, oh, come on, that can't be right. I remembered really complicated formulas for these F tensor. Yeah, there are, but it boils down to that. Wow, that's cool. Which I could just deduce from this sort of argument. This is called finesse.
Finesse.
Right? So indeed, E field amplitude is a frequency too. Okay?
Sorry, I didn't get the Doppler frequency.
The top.
At all. From the no. E.
Oh, this thing. Yeah, we'll talk about that later. Yeah.
It's a relativistic Doppler factor.
Yeah. That is the way I do Doppler, and there's a reason for that, which we'll do off camera, since it's in the colloquium that has to do with Occam's razors and Evenson's lasers. Remember that by any chance? Did you get to see that? Okay. I'll give you one less problem and assign that video. And also we've got the slides online, right? So that's something that's done right in the middle of that talk. It was supposed to be in the first quarter, but the talk expanded, so it ended up in the middle. Yes, that's something really worth knowing, is that relativity has been given to us by Einstein as a second-order theory. He starts with second-order effects. The contraction is a second-order effect, tiny second-order effect for the velocities we're used to. And time dilation, same thing, the expansion of time. Also, second-order effect in velocity. Okay, so here you have the crowning theory of our modern physics, starting off in a very amateurish way by addressing the second-order effects first. It's the only theory I know of that does that. All other theories address the first-order effects first. First things first is a logical, shall we say, saying. Relativity doesn't have that, and that's why relativity is taught badly. You got to do the Doppler first. It's first order, and then everything just falls out. If you're talking about light waves, and you've got to talk about the light waves too. See? Not as corpuscles, but as interfering things. So that's another story, another day, but I'd have you look at it. It's right in the beginning. Okay. The rho is the logarithm of the Doppler shift. If the Doppler shift is e to the rho.
I know what is rho.
Rapidity, or sometimes referred to as a Wigner rotation.
Sometimes, yeah, and it's usually given the letter phi, which I immediately stop. And the reason I use rho is because the other parameter that's really useful in relativity that no one looks at is stellar aberration. This is, of course, a two-dimensional or multi-dimensional parameter. It's the transverse parameter. You see, if you're looking at light, starlight perpendicular to its k-vector, you'll see that k-vector rotate to first order.
Mm-hmm.
So this also
can be in terms of velocity or something else.
Yeah.
Or phi.
Yeah, and then the symbol I use for that is sigma. And sigma is sort of an upside down rho. But it also has S for stellar. So it makes sense. And rapidity is rho for R, Greek R, right? So I'm going to demand that we use those symbols. And since we've got a new way to look at relativity, we can probably get away with it. New terminology. So yeah, take a look at that. Yeah, I think you'll be amused by it. It's really a neat. I sort of have a little allegory, thought experiment to explain it. We can do that just on a separate day sometime if you want to go into it. Okay, So let's do the Feynman number one axiom. Now, we're making a big jump right here because we're saying the stuff that we got from light is going to apply to all of the quantum mechanics things that we're going to be doing in the normal Schrodinger sort of way. That's a little bit spooky, right? But if the big Feynman can do it, I can do it too. Just that I filled in a few more lines than he did, because I made a connection of these amplitudes with electric field. And particularly I connected the Planck axiom to the square of the field, you see, amplitude. So what he's saying is, and he's using the word amplitude, but he's thinking, when he is doing his book, vector mesons or something like that, some weird quantum field as opposed to the electromagnetism that he was so good at. He's on to something else when he does this in 1963. He says, this amplitude of k prime first and j second, that's the amplitude of state j after state k, the initial state, is forced to choose from the available j's, that is, m-type states. M's without the prime are being forced in the choosing. This thing started with a prime. See, this amplitude, like our sines and cosines that we worked out before, is going to be squared to give, this is the axiom, the absolute square, and these are complex numbers because they're wave functions, just like we were talking about a few minutes ago, gives the probability for occurrence in this state J of a system, and this is supposed to work for all quantum systems, that started in the state K prime equal one of these, 1 prime or 2 prime or n prime if it was an n-dimensional quantum system. It might be an infinite dimensional, it can go on forever. And, to continue this, of a system that started in this state, and we're asking for the probability for the sorter that's doing it, is then forced to choose between the final states that are available in this so-called sorter, this polarizer. We write the word polarizer here as far as we're concerned. Okay, so this is a hell of an axiom. Okay, this is where the physics and mathematics meets. Now later on, the other 3 axioms, okay, that we're going to do today, the other 3 axioms are more like mathematical ones. That is, this is the big kahuna here in the sense of physics. And we've justified it by Planck's axiom for light. So we're extrapolating from that to any system. So this is a big jump, big logical jump, big physical logical jump, that this would work for every field, not just the electromagnetic field. But now if we can get really smart and show that every other field is just made out of electromagnetic fields somehow, that's really stretching. But then you'd say, oh yeah, this makes sense. But right now, it's a big jump. And that means it's going to work for spin. Okay, now we got to talk a little bit about that just to get started here. These amplitude axioms, 1 through 4 that we're going to do, but particularly number 1, apply to all intensity probability conserving systems. Now that's a mouthful right there. We're saying that when we do an analysis, nothing gets lost. Everything that comes in here can be accounted for either in X and Y polarization for the counts that we were doing before, or spin up and spin down electron polarization. This is just a view of a Stern-Gerlach magnet, non-uniform magnetic field causing these things to polarize in various directions. So when we do a square of one of those, spin up along a certain angle compared to spin up in the laboratory, that's going to have an angle associated with it. But what you've got to realize is that that angle that they usually measure for an electron polarizer is twice the analogous system that we're doing, which is the polarization angle theta. So I've got a few pictures here that show that. This is all figure in Unit 1, Chapter 2 now, that's going into this thing. So the electron spin vector S tilted by this angle beta is going to use the same mathematics as we are for our polarization. It's just that we have to remember that the electron spin angle of tilt is 2 times the angle theta that the E vector is tilted by, the one that we were using before when we wrote our sines and cosines. Now we're going to have to explain why that is as best we can later on. I just want to warn you about it because I'm making a claim here, particularly with these animations, that we can describe both of them in terms of spin vectors. That's something we will do very carefully later on. That's a very the heart of our SU2 group theory, is making sense out of that. So, if you're doing electron polarization and using the angle theta as your parameter of, shall we say, polarization, and this is the Y polarization and this is the X polarization component, okay, then when it comes time to make connection between what happened in that optical experiment with what happens in a spin up, spin down spinner system, where this angle theta is beta over 2, you should never forget that that's a big connection. Now, I think I say something about this, yes. This is why this has to be. When down is only 90 degrees from up, see here's spin up, and we're drawing a picture like this one of another axis that's orthogonal to this one, and we call it spin down, then you'd better have a factor 2 in the denominator for your angle. That's it in a nutshell, the connection. But this is, I think, one of the most beautiful physical mathematical mysteries, is the connection between ordinary rotations in real vector spaces, if you want, right? But they're complex too because they're oscillating, right? These things are all jittery, like jittery children, okay? And so are these, okay? So you got complex numbers for components in both these dimensions as you do here. So the mathematics of these two is isomorphic. I mean, it's one-to-one and onto, as we used to say about mappings. And so when we talk about X and Y polarization, we will be using virtually the same bookkeeping, except for this darn factor of 2 between these angles of electromagnetic polarization and the electron spin orientation. Now the simulation that's over there has a spin vector. That spin vector is designated by S, not because it stands for spin, because it stands for John Stokes' last name. It's called a Stokes vector in electromagnetic optical theory. So what you see there is a Stokes vector being transformed by various analyzers in the animation. And that's what we're going to spend the next 2 lectures talking about in great detail. And then later on we'll make a group theory for it. Okay. Now, I wanted to just show some sample calculations that you can do without having matrices. This is very down to earth. you want to, in this case, analyze, I should say you're really sorting beams, but each time you use one of these little calcite crystals or a Brewster polarizer, you're going to get 2 beams for the price of 1. And if you use another one, you're going to have 1, 2, 3, well, I should say 1, 2, 3 beams, but then if this one goes into an analyzer, you'll have 4, and so forth. You're going to do 2 to the n, where n is the number of splitters. And so this could get, you know, a lot of different beams going that all have different intensities. And intensity, of course, is the square of the amplitude, according to just classical electromagnetism, but then axiom 1 of Feynman is demanding it just on the face of everything. So here's what you do. You take these parameters that we had, cosine of theta. This one came out to be a sine. This one came out to be a minus sine of theta. And then there's cosine again right there. So here's the transformation matrix that Feynman bases all of this stuff on. And what we want to do is we want to figure out how much light we're going to get here if we do another 30-degree analysis with an x-axis this way, okay? And then this one has already been tipped, you see. So these are the x prime states that we're dealing with here. Now let me see, the way this is going is we start with x-polarized light, we force it to go through an x prime analyzer, so these are the final states for this thing. So we're going to be having amplitudes here and here given by squares of these numbers. So let's look at that. Each time we do this, we're going to start with initial base state, in this case is x. It's got an amplitude 1 and a probability 1, and we're going to sort of go through this thing stating what happened at each stage. Okay? So, if we're going to look at this channel right here, okay, we're looking at an x prime polarized light. That's the final, shall we say, base state that is going to come out of this x prime analyzer and go into an xy analyzer right here, you see. That's just showing you where the x prime axis is relative to x, 30 degrees, difference just like this one. Okay? So when we got an amplitude x prime x, okay, that's square root of 3 over 2, 0.867, but we're interested in probability or intensity, which is the square of that, 3/4. Okay? So 3/4 of the light is going this way. Only 1/4 is making it out the bottom there. If, in fact, the energy is conserved. Nothing gets lost. And that's what's understood for all of these analyzers. Nothing gets lost. That's called unitarity. It's a unitary matrix. Okay? So, if you want to look at what came out the bottom and check your mathematics, okay, it'd be this guy right here, minus a half, okay, y prime x goes to y, okay, with a minus sign. But if you square it, you don't care. That's all you're going to observe, unless you have a phase-sensitive detector. Okay? So the probability is 1/4 plus 3/4, that's 1. Nothing got lost, right? You see, it's really simple stuff. This is stuff that could easily be taught at the high school level, but certainly at the freshman, sophomore level. But they don't. They go do the Bohr, ring or something like that. They don't know what the hell they're doing, right? This is something you actually look at, right? And you get to be working at root level of the theory, the direct notation. And the group theory comes very easily with it. So, sales pitch. Okay, now, next stop. Okay, take all of this and say, I'm going to ask what comes out of the x. Right? I'm going to put this little collection right here. This says the base state, and this is the amplitude to make it through this little rise right here. Okay? So now we've got two amplitudes. The one we worked with before, and then those things. That's one of the axioms that's coming later. Those have to be equal. Okay, so they're both square root of 3 over 2. So I get 0.75 here, but the probability is what you want, so it's 0.75 squared, which is a little over a half. A little over half of what you started with is coming out right here. Okay? And then we can do the bottom one too. Okay? Now we're going to put y there, right? So now we need a y(x) prime next to an x prime. Square root of 3 over 2 that we had before. And then 1/2 coming from the y x prime. Okay? Now, you might say, hey, wait a minute. I got y x prime here, and I got x prime y here. There's one more axiom that comes next. The second one is that that is the complex conjugate of that. And if it's real, it's the same. So I would use a plus sign for that one. Okay? But anyway, a half of the square root of 3 over 2 is 443. That squared is this. Okay, now this doesn't add up to 1 because we got this guy down here. But when you add that one in there too, it does add up. Okay? Sort of thing. This is the way you do quantum mechanics if you don't want to mess with matrices, matrix algebra. But you can see it can, you start putting these things back together again, which is what we're going to do next. It becomes a forest of possibilities, and you're disorganized. You won't be able to carry this very far. Anyway, let's look at the other axiom. This is the one. Conjugation or inversion axiom. I call this time reversal symmetry. I don't even like that, but that's really what it is. The second axiom concerns going backwards through a sorter, or a reversal of amplitudes. Axiom 2 is that the complex conjugate of this jk prime is equal to k prime j. Okay? This complex conjugate of this amplitude must be equal to this flip, to the flip to k prime j. Now, the question is, how do you prove that? Well, we're going to put that off for a minute, but basically the idea is you run the clock backwards and watch the waves go the other way. This is the one that more obvious. Okay? If identical analyzer used twice or more, the amplitude for a past state k is 1. And this figure comes right out of the old textbook. It just says that if I polarize a beam, that, in other words, this one right here could be unpolarized completely, but it got polarized here. If I check it again with the same analyzer, not one that's tipped, if I check it again, they're all going to take the top row forever. No matter how many analyzers, these are perfect analyzers, okay? So nothing gets lost, nothing ever comes out of the bottom doors, or if it's a multi-dimensional system, nothing goes to other states. Once you've polarized, it's good forever. Now that expression is called orthonormality. We'll see why that is later on. We'll make sense of that. But it's really very much a statement about the experiments with polarization, with perfect polarizers, which I might say. Okay, now we just have a little bit of time here. I'd say 15 minutes, or maybe 20 at the most, given that we started 10 minutes into the normal class period. So we will have time to get through this. And this is really weird. This is where axiom 4 is going to be shown. A beam analyzer, the way Feynman would look at it, if he did polarization, would be actually a Mach-Zehnder interferometer, but I'm not going to get involved with that right now because this is one that you can actually build very easily. Just buy 2 of these Brewster polarizers and put them like that. And if the optical path length for this one is the same as this one, this analyzer will do nothing to any beam that comes to it. Pick any side polarized, any angle, any ellipse. You can make an elliptical thing to come into this thing. General state of polarization can come into this thing, go the separate ways, and then recombine and give you exactly what you put in coming out. That's the really an amazing piece of optics is what this is. Now you have to be aware that if I so much as go up to a thing like, say I got it so it's working, I tried all polarizations here and I got them to be the same here. It's all tuned up, right? And that's not that hard to do because all it cares about is where on the phasor you are modulo 2 pi. So as long as I have an integral number of wavelengths here and here, it's going to work. So you don't have to, you're talking about, fraction of a meter here, and the light waves are fractions of microns, right? So you're talking about a factor of a million. And if you had exactly a path length within a millionth, we'd probably never be doing the kind of optics we are. But you only have to get it right 2 pi. So you just adjust something really carefully and boom, it'll start working. That's the way laser cavities work. It's the same thing. So what we're going to do is, with an analyzer, see, we're taking this thing apart into its separate orthogonal states that are not the same basis as it's in, and we're going to speed up or slow down the path length just a little bit to add an extra phase, so we're going to get a different polarization over here when we do that. This is called the sensitive region, where you can just go, if I were to set this thing up so it was perfect and go up and go, just puff at it, it would go crazy. Right? It's really sensitive. Even in visible light, the higher frequencies, it's terrible. Right? You're doing electrons that have really short wavelengths. It's really sensitive. So it's sensitive to this extent. Doing microwaves, you can kick it around, and it'll still work. Okay, so this is what is being simulated. We split, we play games, we put back together again. That's what you're seeing on the screen there. Is you're seeing a couple of analyzers, 3 analyzers. One to start with that takes a polarization, and if you can frame that enough so you see the detail, you'll see that on the extreme right here, a beam of light is coming in with a polarization that is tipped by, well, I've got 40 degrees written there. The beta angle that we talked about is 40. We're using the electron notation here. Let's see if I can make this thing respond. Oh, I've got the wrong computer. Here we are. Okay. So if I put this thing with a 0 angle for the input polarization, that is, make it X-polarized, okay, you'll see that what the analyzer did was it sent all of the light to the top. And I'm going to speed this up a bit here. So each time it goes, the light goes all through the top, 100% up, because it was X-polarized by something down the way there. If, in fact, I send it in with Y polarization, which is about here, I think, that looks good. Well, it's 80 degrees. I'll try to get 90 degrees. Let's see. Oh, I'm sorry. That's I have to go, this is beta, I've got to go twice beta up here to get a 90 degrees polarized light, okay? So theta equal 90, beta equal 180. And that isn't quite 180, but I think I can make it good. Okay, seeing it works pretty well. So this time, all went to low row. Okay? So the analyzers are capable of putting arbitrary amounts in the top and the bottom, depending on how you put how you affect the input state here. Let's go back to beta equal 90, which is a polarization of 45 degrees. Okay, beta over 2. There's a 45 degree polarization. You see equal amounts in both channels. And then this is a do-nothing analyzer, so I get the same polarization coming out. And that's what's shown on this slide that we just looked at. Okay? And this is basically the same analyzer, a 0, 0, 0 analyzer. That's the one that's corresponding. And in the spin world, it's the one corresponding to the spin on what we call the B axis. All this stuff, all this notation, A, B, and C, will make sense later on. Basically, A is what Pauli and Jordan of the spin world would have called the Z axis. We call it the asymmetric diagonal, A for asymmetric. B stands for bilateral balanced axis. That would be the x-axis in Pauli's world, and in Pauli's Y would be the C. C stands for circular polarization, or Coriolis, or a current, or complex. There's a really nice mnemonics associated with this. It doesn't look like much at this point. In any case, that's the situation over here that we're dealing with. This is a 60-degree polarization here, and I can go ahead and try to set that up over here as well. What I've got to do to get 60 degrees, I'm sorry, wrong computer. What I've got to do to get 60 degrees is get closer to 90 and have 120 degrees there. I think that is right. Oh, wait. That's beta equal 120. I've got to go the other way. That's down here a ways. Let's see if I can get that. There's beta equals 60 right there. Corresponds to a 30-degree theta angle. Okay? This time you've got more stuff going across the top than you do going up the bottom. I've sketched this one in very carefully. So this is the filter that's got a polarizer associated with it that's in the x direction, and this one's got a polarizer that's accepting y and rejecting x, basically. But there's a lot of magic going on right here. That's the Brewster polarizer right there. Okay, and then there's another Brewster polarizer here, except it's taking input on its output and giving output on its input. And as you can see, with no activity, with nothing that's changing the phase of these two channels, it's going to recombine and give a polarization. And it should work backwards, you see. That's the other thing you like to study with these things, is time reversal. So it's a pretty neat machine to have to look at this stuff. Okay, now what I want to do is state Feynman's axiom. I think I can do that, and then we'll be taking this thing apart. This is the fourth and final axiom for unitary quantum mechanics. And if you know anything about group theory at all, you know it has 4 axioms too. And we've already, after we finish this one, stated it. It's just to kind of do it backwards. So that's really the point I'd like to make today and the next time on Tuesday, is that the group theory is in quantum mechanics. This would be the associativity and closure axiom sort of all together. The fourth axiom concerns do-nothing property of an ideal analyzer. That is, the sorter followed by an unsorter. This is the sorter that splits the beam, and this is the unsorter that puts them back together. I really clumsily stated a name for this thing to be the put back together verb. Okay, and sketched above. Okay? So the ideal sorting followed by ideal recombination of amplitudes has no effect. That's the statement. So if you start with a state M prime here, polarization using a primed sorter, okay, has been downline and made this initial state, and then you send it through all of the open channels. We only have n equal 2 here, but this is supposed to work for analyzers that split things up infinite number, possibly. Anyway, after you've split it, and then you ask it to recombine each of those k and make a choice of all of the possible j prime prime, you will get exactly the amplitude you would have gotten if you just left this stupid thing out. This thing has no effect if it is making the paths equal. And that's a bit of optics, that this splitting process is time reversible to as perfect as we can expect from laser optics. So again, this is kind of a time reversal symmetry axiom, because it's supposed to work both ways. Okay? Now this is a figure directly from the old book, but basically it's saying I'm going to get the same number of counts in each of the channels when I do the experiment with this beam coming in, or have that same beam come into a thing like that and come back out again, and it's going to come out the same as it went in, as far as you could tell. Obviously you can add an overall phase, because we're only talking about squares of these things, but we're making statements about the amplitude without the square. So that's a bit of a jump. Okay, is there anything more I can say that you can think of that has a question? Now, if I will use the remaining time to just look at, first of all, let's make sure our axioms are consistent. Okay? Let's do a special case. This is a matrix element M prime J double prime. Let's just do J double prime equal to M prime, okay? Now we already showed by orthonormality that that thing should be 1. Okay? And then by axiom 1, okay, we use the one here, we can say, all right, I'm going to go M prime K, and then K M prime. Well, that's the same as M prime K star, right? Okay? Well, what it's telling you is if I sum over all of the probabilities, I should get that. This should be 1, and then by the second axiom, which is time reversal, this becomes that, you see, and then this axiom says, yeah, that should just be M prime, okay, which is 1. So it's consistent. But you don't expect to find proofs of entire axioms. This is only proof of one special case. Good thing to check, but that's it. So here they all are. This is the collection. This is what we start our group theory with, as well as our quantum mechanics. Now, the rest of this we just looked at a simulation like this one. So I've got the thing turned on the side there a little bit. With beta equal minus 60 degrees in this one. Okay. And I've got a theta n equal 100 here coming in. That means I've got a 2 theta, which is beta of 200 coming in. It's just another example. And I think what I'm going to do with that one is do the actual amplitude algebra. Now I'm going to have you go ahead and look at this on your own. This is the same as what's in the textbook. So this is a chance for you to just read what happens as we have an input polarization here of theta equal 100. It goes through this thing that's tipped by minus 30 and then comes back out again, and then we can analyze and sort it in the final analysis. So you see, the idea of the simulation is that very often I use these analyzers as sorters. So this is just going through the same analysis that we went through before, except now with algebraic expressions for sine and cosine. And the idea is to see that the x output and the y output comes out to be just the same as what went in. Just checking the trigonometry of the wave interference. So the conclusion is this is a do-nothing analyzer. In fact, does nothing. This is the same polarization as that. That's just looking at it with an example. Okay, time for do something. First of all, one of the things you can do with these optical analyzers is turn them into murderers. Let's turn one of these analyzers into a murderer. The way you do that is you reach up and you click in the window here. Now that's a peaker. That's a little thing that's adding a random phase to the wave as it goes through. So that's where you look at the beam. You do something to tell whether the beam went by or not. But in order to do that, you've got to shift that phase, usually randomly. That we'll talk about later on. But if you click again, it just stops it and starts counting. And so that's a half murderer. A polarizer. That's a polarizer, you see. Now this beam is acting like a polarizer. It's only letting through Y polarization. And not every time, because there's a lot more going to the upstairs than the downstairs. And the calculation for this gives a prediction of 0.75 probability to quarter. 3/4 to quarter, you see. So if that's true, this should be 3 times that, and it's not, because it's random. And the comparison of the calculation, the actual output, and the total there, those little bars there are interesting in what they give. But this is just checking to see, you know, this is way an experiment. It's a simulation of the quantum mechanical probability at work here. So if I just stop it right here, there's a looker, that's this thing. This is just a counter. I didn't even need to click that bottom thing, it counts automatically. Once you look at the thing, you can make it count. So this, you can let this thing run. And since we have a small number of students, namely 1, you're welcome to borrow a computer that will run this if you want to, you know, sort of mess with it. Okay?
Just I cannot understand what happens. You change the polarization, polarizer, the direction of polarizer.
Yeah,
there?
this is just doing nothing.
Yeah, no, the
So
last one.
It's making this polarization.
Yes, the last one. I'm talking about the last
this one.
Yeah, what
Yeah.
happens there?
Oh, I actually have photon counters in effect here.
Photon counters?
This is why I call it a murderer.
Oh, sometimes it passes through that way.
Not now.
It doesn't pass.
No. When I had it open down here, it did.
Yeah, just it count it
Yeah.
counts photons.
Yeah,
Just this.
that's what it's doing. Every time things are right, and that's the big mystery is what is it that's going on to make the thing forced to choice, right?
Yeah.
That's the real mystery of quantum theory. Which we would like to know more about. And you have to be aware that the phase of the light can go infinitely fast. In fact, it wants to go infinitely fast. So you got to realize that the amplitude here is buzzing at, if it's a optical thing, it's buzzing at 600 terahertz. It's pretty fast, but if it's an electron, it's buzzing at exahertz. So this system is just an incredibly high frequency thing that's, beating, and the beating is occurring not only with the light components that we know about, but also with all of the quantum mechanics of the mass of whatever it is that's holding these various devices like counters in place. So there's a great war going on every time it's forced to make a choice. Back and forth, they're talking, back and forth, back and forth, back and forth, back and forth, back and forth. Trillions of times, and finally something happens. Something is just a little bit a favor of saying, okay, we're going to take it this way. And that is called the measurement process, which means really not too much, because we don't know what it is that gets. But that's what's so cool about the Feynman method, particularly if you break it down to two-state systems, is it really shows from the very beginning what it is that we do when we do quantum mechanical experiments. I predict 3/4 and 1/4, you see, of however many I put in. I put 160 in here now, you see? And the question is this thing really 3 times this one?
No. It's a little...
Not.
It's a little less.
Yeah, on the average. I have to get, millions of counts here before I can chop off the figures and see a 3-to-1 for what I have left, right? Yeah. That point really has to be made when you're first coming into quantum mechanics and dealing with it the way we do in the lab. That's a real experiment that could be done, is being done in much more sophisticated ways as we speak. Now it's getting pretty close. It's 50 to 150, but it'll never be. Now, of course, with a computer, if you start with the same thing, I'll be doing random number calculation, right? And I'm not making that random number calculation random. I'm not putting the temperature or something into that. You see, I could do that, and then it would never be the same. If I start this over, we will get to a point where we have 59,166, right? You'd never get that in a real experiment. Okay. Now, there's the murderer. There's the filter. You leave it open. Okay? So it takes whatever this is, throws away on the average whatever 3 times as many get stuck here, but roughly every 3 shots you should get 1 down here on the average, you see. So this is a block to give you only Y polarization. No matter what comes in here, this thing is set to X and Y, so I am going to, if I leave the bottom window open, always get Y here. Okay? So that's basically this thing, right? Polarized sunglasses. Getting rid of that bad stuff that comes off of the road, X-polarized, right? And it's blocking that. So you can drive without blinding yourself off of the road. Okay? Now, half-wave plate. This is interesting, okay? I put in a phase lag here, okay? Do this real quickly. I put in a little bit of a phase lag there, and watch what comes out, okay? I've got it going through both doors, so I'll get something if I put in even a little bit of phase. Elliptical polarization. Okay? There is more tightly elliptical polarization. Even tighter, right? That's almost plain polarized, but it's got a little bit of activity to make it get a bigger and bigger ellipse until finally I get circular polarization. That's called a quarter wave plate. I make that thing, well, we're not quite there yet. We got to go to 180, I think, in order to get that. Let's see, is that right? 170? What's coming out? Oh, no, this is the one, this is the full half wave plate. This is a quarter wave plate right here. That, I'm sorry, right there, I think. Let's see. 100, or is it 90 I want there? I think that's, there you go. So there are circles coming out of there. Okay?
Why do, what, if it is circle?
Yeah, let me jump ahead here. This is the quarter wave plate where you're getting ellipses coming out. Here's a detailed calculation which I'll go through. This is a cool way to look at it. Okay? If I put an extra phase between this phasor that's making the x go back and forth, that's what this is doing. This is the x position here. And then I put the y position, turn the phasor on the side, okay, and put an angle, say 45 degrees, okay? I get this. You see, so that's the geometry of what's going on when you put that extra activity angle into the thing. And we're going to, that's another thing we're going to study in great detail. This is the geometry of U2, unitary 2 group, as far as physics is concerned. So again, this is what you get to look at if you use polarization. With the Feynman approach, vector mesons, all you get is some numbers. You don't get to actually see the trajectories of the polarization. And we also get the spin vectors doing things. You see the thing rotating there. That's what this angle really is. This is a rotation angle of a Stokes vector. Or if it was electron polarization that we were simulating, a rotation of the actual spin vector. Okay, this is the problem that I would have you look at. It's on page 40 of the text. I'll go ahead and print this out so you can just write on it. And you go through this, you'll have redone everything that we've done in the lecture today. So it's a good one, and I have the answers written somewhere, but don't look for them. Instead, you know, actually do the thing and see if you can get. You can see a picture of what's coming out, so you'll know if you're on the right track, right? So, okay, I think that's it for the thing. I'm going to go ahead and print this.